Hi, I'm Abrar, and I'm here to present to y'all about the research I've done as an intern with Sandia National Labs on evolving spiking circuit motifs using weight-agnostic neural networks. My work is motivated by neuromorphic hardware. Most of us should be familiar with the typical formulation of an artificial neural network, where there is a dense communication of continuous values between layers of neurons. In contrast, a spiking neural network loosely mimics biological neurons by using discrete spikes to transfer information across neurons over time. This spike can be thought of as a threshold activation function that discretizes the output of a neuron to be 0 or 1. Neuromorphic hardware has energy efficiency advantages compared to traditional hardware when using SNNs. Converting ANNs to SNNs is relatively difficult, but some ANNs are compatible with neuromorphic hardware, particularly ones using threshold activation functions. Neuromorphic hardware tends to vary in implementation from vendor to vendor. To work towards algorithm hardware co-design, I investigated using weight-agnostic neural networks to generate sparse network topologies. Weight-agnostic neural networks, or WANs, by Adam Gayer and David Ha, uses a large set of activation functions and an evolutionary-inspired search to generate neural network topologies that perform well. The image to the right describes their algorithm. Essentially, a sparse topology is tested over a range of weight values that are shared across all neurons in a network. These topologies are then ranked by performance and size, and then are randomly mutated by adding new connections or neurons. Unlike the WAN paper, we limited our search to linear and threshold activation functions. Combining these activation functions, these networks can be approximated on neuromorphic hardware. To ensure a fair comparison, I ran 3 tests from the original WAN paper, the swing-up cart pull and bipedal walker tasks from OpenAI Gym and MNIST classification. We can see the resultant topologies for 2 of the tasks here. A simple approach could have used a fully connected neural network, but instead we see the outputs of the spiking WANs to be a sparse topology. As for results, we measured several tasks on both the WAN and spiking WANs. The tuned shared weight is the single best shared weight value for the resultant topology, which can be seen in the first column of the WAN and spiking WAN sections. The tuned weights are when a population-based method is used to individually fine-tune the weights, seen in the second columns. I found that the tuned shared weight topologies perform better on the control tasks compared to the spiking WAN. However, the fine-tuned weights perform slightly worse. We believe this is caused by the smaller network sizes found in the spiking WANs. There are numerous paths on extending this work. Currently, we're looking into mapping these networks onto physical neuromorphic hardware. Also, WANs by default minimize the size of the network as a rough approximation of energy usage and complexity. As mentioned earlier, neuromorphic hardware comes in different flavors, with some platforms restricting the number of connections for more neurons and vice versa. It would be interesting to explore developing energy-based constraints that target specific hardware platforms for neural network hardware co-design. Lastly, WANs are trained over numerous shared weight values, which allows the network to be weight agnostic. Some low-power neuromorphic hardware introduces random noise onto the synaptic weights, so I've been exploring the potential for noise resilience in the input space and in the synaptic weights of these networks. Thanks for listening.